Please welcome author of Water 4.0, Professor, and Director of the Institute for Environmental Science and Engineering at UC Berkeley, David Sedlak.
I think I've hit Water Nerd Central because I was expecting that by this time in the program, people would have jet lag, people would see the sunshine outside, they'd get smart and they'd leave. But that's not the case with this group, and I think that's because they're really excited about water and solving the world's water problems. I've been very impressed by what I've seen here the past day and a half because I think I've found some of my tribe that I didn't know existed. I think this is a group of people that I don't often see at conferences, and I'm just inspired by what I've seen. And I'm inspired by the spirit of sharing that you have because, you know, the innovators told us about their innovative research. The users told us about their needs. And Paul gave us a preview of the movie. And so this spirit of sharing seems to permeate the place. And, you know, along the lines of that, I realized that I needed to share something with you. And I couldn't share Water 4.0 with you because Paul's given everyone a copy of it. And so sharing something that they already have on their shelf seems like a poor idea. So what I want to share with you are the thoughts that I have in mind for if I ever get my act together and write that next book. And what I want to do is kind of show you like the director's equivalent of the rough cuts of kind of what's running through my mind as I'm thinking about what the next water challenges are and how to explain them. And so what I ask of you in the spirit of sharing is to share your opinions with me afterwards, because I think this group, actually, I'm actually rather nervous speaking in front of this group because I can't pull the wool over your eyes. You know so much about this field. And so I want to hear from you over mojitos about what resonated with you about what I say and what I got wrong and what you think should be included, because this may eventually become the next thing. And so you can see the title here, BlueTech Solutions for the Second Half of the 21st Century. Wait a minute. The 21st century just started. What are you talking about the second half? Well, if you think that the 21st century just started, you've been asleep. There's been 19 years we've been through, right? Seems like it went with a blink of an eye. And the work that the group here, the BlueTech group, is doing is really laying the foundation for the water infrastructure systems that we're going to have in the second half of the 21st century. That is, the work that we do as innovators, early adopters, entrepreneurs, researchers, sets the framework, and then others go and implement it and build it. And so with that in mind, think about this. If you were a student starting out in business school, or you wanted to learn about innovation, one of the first things you'd learn about is the S-curve for technology diffusion. How many of you here have seen something like this before? Pretty common, right? So those of you who haven't seen it, the idea here is that technologies diffuse out. They go from invention to prototyping to demonstration to early adopters, and that y-axis there are the number of units that are installed, and the x-axis is time. And so over time, you have this period where there's kind of a run-up where people are figuring things out and making mistakes and improving. And it's only the early adopters, the companies like what we have in this room, who are willing to spend the money to do these things because they want to be ahead of the curve and they want to do things right. And later, after they've proven it, others say, oh, well, we could do that. We want one of those too. And so it grows over time. Now, if you think about the S-curve and you think of one of these things here, it was a couple of years from going from a sparkle in Steve Jobs' eyes to coming out in the market. And within 4 years, we went from iPhone 1 to iPhone 4S. And, you know, frankly, in my opinion, things haven't improved much since about 4S. So there's an S-curve where we go from technology invention to prototyping to wide application, and the time period is about 6 years. In the water industry, because of the low return on investments, the reluctance to take risk, the long lifetime of equipment, that x-axis is greatly expanded. Things like nutrient removal technologies have taken 30 or 40 years to run through the S-curve. And that's why I think we're designing the technologies for the water infrastructure of the second half of the 21st century. Let me give you an example from my own life. I tend to conduct research related to potable water reuse, and it's hard for me to believe I started doing this work 20 years ago or so, when there really weren't a lot of potable water reuse projects around. There was LA County, there was Upper Occoquan, and there was Orange County Water Factory 21. But over time, more and more plants got built. And so you can see these are data that comes from the NRC report on potable water reuse. And you can see here that it slowly grew between the years 1960 and 2018 or 2020. And I chose an interesting scale for the axis you can see. So I scaled this based upon these two blue arrows on the right-hand side. The first one, the amount of wastewater in the United States that's discharged to the ocean. So say you really don't want to recycle water that would go into a river that someone might use downstream, but any water that is quote-unquote wasted to the ocean is fair game for recycling. And then I put a second arrow on here, recognizing that there are some parts of the United States that probably will never need to recycle their wastewater. Think about the Pacific Northwest, think about New York, think about Boston. These are places that are quite wet, and they have an adequate water supply. They're more worried about stormwater runoff. So say about half of the United States, California, Texas, Florida, where the wastewater goes to the ocean, might be interested someday in recycling their wastewater. So we haven't made a lot of progress, but you can see in the last decade, the rate at which we're building these treatment plants has ticked up. We have things like a project going on in Virginia that will be larger than Orange County. We have El Paso. We have various projects popping up in Florida and Texas and California and Colorado. And so we can imagine how the scenario will play out between now and the second half of the 21st century. Let's expand these axes to 2050 and think about one scenario where it kind of peters out. Maybe this has run its course. Maybe people find another way to generate water. Maybe regulatory barriers prove to be insurmountable. That's one possibility. Another possibility is things keep going on the current trajectory. We keep building potable water reuse facilities, and by 2050, maybe close to a third or more of the possible places where we could recycle wastewater as potable water reuse happen. And the third scenario is it accelerates. So think about that. Between now and the second half of the 21st century, somewhere between, I don't know, like 25 and 75 million people in the United States might be getting their drinking water from a potable water reuse project. That's pretty cool. But look how long it took. Look how long that life cycle was for the S-curve. So when we talk today about the closed loop system for water reuse in factories, when we talk about solutions for developing countries, when we talk about all the things that we've been talking about these tables, we have to realize that we're on the left-hand side of that S-curve. But what we do now is going to determine the trajectory of all these technologies as we move to the 21st century. And that's really important because we're really going to need them in the 21st century because things are going to change very quickly. Now, before we think about like how it's going to change or why it's going to change, I want to think about who the beneficiaries are going to be of this change. And I want you to think about income distribution around the world. So this is a figure from Gapminder. This is the website that Hans Rosling and his daughters set up after those great TED Talks that he gave. And what you can see here is that it charts the average daily income of people around the world according to the continent they live on. And Rosling breaks it up into 4 different categories. On one end of it, you have the rich people. There are about 1 billion people on Earth who live at an income of somewhere around 12,000 US dollars per year and more. And there are about 1 billion people on Earth who are in extreme poverty, maybe less than about $1,000 a year or more, or less rather. And in between, we have about 5.5 billion people who are living in Asia and South America and Eastern Europe who kind of fit in the middle. And these people will largely be the beneficiaries. And the other thing that really comes out when you think about the changes that have happened in the world's wealth over the past 30 years is you can see that the picture is quite different. 30 years ago, we wouldn't see this figure. We'd see the figure on the left-hand side here. Most people on Earth were quite poor. And so when we talked about people living in abject poverty, people who didn't have access to water, they were people who had less than $1,000 a year to work with. Now, the majority of people on Earth have more money. And if you see the trend that's going on here, 30 years from now, there are going to be more people with more money and fewer people living in abject poverty. So here, I'm more optimistic than even Paul is here because I believe that we're on a trajectory. It's going to have some bumps in the roads of global development where people become wealthier over time, and that wealth is going to allow them to adopt some of the technologies that seem to be out of their reach right now, and probably could be out of their reach forever. The other thing we have to think about when we think 30 years in the future and the people who are going to use these technologies is to think about why they're going to need them. And we've all been talking about urban water challenges and urban water security as an issue. These two figures come from a paper that came out last year that looked at about 25% of the cities in the world, and looked at those cities that were supplied with surface water and those cities that were supplied primarily with groundwater, and asked the question, what is their water supply going to look like in the second half of the 21st century? Now, surface water cities, right now about 15% of cities that rely upon surface water have a shortage for 1 month a year or more. And in terms of groundwater, maybe 20% or so of the cities have a falling groundwater level in their city, which means unsustainable groundwater management. But over the next 30 years, we're going to see continued migration to cities. We're already in this period of great migration to cities. It's going to go from, 52% to about 80% of people living in cities. And we're going to see climate change having an effect on water supplies. And so for surface water cities, this study showed us that if the cities have first priority for the water, something like 27% of the cities that use surface water will have a shortage 1 month a year. And if they don't have first priority, if they have last priority, because industry and power generation and agriculture have those water rights, it's close to 50%. And with respect to groundwater, of the 482 cities that they looked at, 230 of them were predicted to have falling groundwater levels. So if you look at the map, obviously the people who live in the cities with the red dots are in bigger trouble than the people with green dots, right? That's how all these things work. So people are going to be becoming wealthier. Cities are going to need more water. So that's a recipe for thinking about water. And I want to think about it from the standpoint of why I'm actually not that interested in Water 4.0 anymore, because I feel like in some ways it's a solved problem. That book was about water for rich people who live in cities. But what about everyone else? Well, I think that the story of how people who are wealthy have solved their water problems is very instructive as we think about the rest of the world and how they're going to use and repurpose these technologies and use them in ways that we never thought possible. So I plotted here per capita GDP in dollars versus population size. And I chose a number of cities around the world that are interesting to me because they're water-stressed cities. And I just want to show you that different cities in different parts of the world come to a different set of solutions. And those solutions are dictated by their geography, their geology, their culture, their legal and regulatory system. But they find a way to solve these water problems using some of the things that I described in Water 4.0. Seawater desalination, water recycling, stormwater capture, conservation, all of the things that this group has been talking about for the past couple days. So I'm from the US. I work with cities in the US, and so here's a smattering of cities where we've really addressed some of the big water problems. And you can see, with Los Angeles or San Jose or Atlanta, these are wealthy, large cities that have largely gone the path of conservation and water recycling to provide their water supply. And when you look, San Diego, they built the desal plant in Carlsbad, or El Paso, they're doing inland brackish water desalination, and they're using water reuse. But their incomes, the per capita incomes in those cities run from about $40,000 to $90,000 a year. Let's look at Australia and Singapore, right? We heard a bunch about Singapore already. Wealthy place, big city, solved their water problem with the 4 taps. 3 of them are new, right? So we've got seawater desalination, stormwater harvesting, and water reuse. And Australia, maybe Perth, has solved their problem by building lots of desal plants and now potable water recycling. Sydney and Brisbane and the rest of Australia, if the drought gets worse, will probably adopt similar kinds of solutions. And again, those made sense in Australia given the context of how they fund infrastructure and what the public wanted. We can go to the Middle East and see that it's been all desal all the time. That is, the water supply issue has been largely addressed by building desalination plants. In Israel, they're using their wastewater for agriculture, but a slightly different approach, similar kinds of solution, again, largely relying on reverse osmosis membranes. Now let's look in other parts of the world. Think about China for a minute. So Hong Kong, if they had a problem, they're wealthy enough that they could probably just adopt some of the same technologies and follow the model that Singapore did. But they're in love with their seawater toilet flushing system, and they have imported water coming from China now, so that's not an issue. But Shenzhen and Guangzhou and Beijing, they may not be wealthy enough to afford these technologies. So they're still waiting on them, and they're building big projects like the South to North project, where they're muddling on with the water that they have. If we look at Europe, we can see our big cities on the Mediterranean struggle with water, but investing money in desalination and potable water reuse, that may be a little bit expensive considering what they typically spend on their infrastructure. I mean, again, it's going to vary from country to country, how much debt they want to take, what they want to do for public services. And if we go to the Americas, we can see Mexico City and Sao Paulo, mega cities with big water problems, but they haven't made these investments yet because they're just too expensive. And then finally, when we move to South Asia and parts of Asia outside of China, we have some very large cities with some very big water problems, but they don't have as much money. So how can we solve these problems? Well, if the cities in the band between 40,000 and 80,000 have largely solved their water problems with these big infrastructure projects involving new technologies, and the other cities, it's out of their reach, it's our job in this room to drop the price of providing water to those cities by a certain amount. And so I'm part of a team that's being led by Lawrence Berkeley Lab called the National Alliance for Water Infrastructure Innovation, NOWI. You can see the emblem there. And we're thinking that we can get 50% reduction in the cost of desalinated water and water reuse. And we'd like to shoot for 90% over the long term. Think about it. If we could drop the cost of desalination, water reuse, stormwater capture, if we could make conservation feasible for a lower cost, suddenly millions of people who are getting wealthier will be able to adopt these technologies sooner. Do you think we can do it? I'm pretty convinced we can. I'm pretty convinced that now. But when I wrote Water 4.0, I wasn't convinced. And I wasn't convinced because I had read this paper from Meni Elimelech and his group, where they had a review in Science of the energy used for seawater desalination. And they showed that over the past 30 years, the energy required to desalinate seawater had dropped and dropped and dropped as we came up with better membranes and pressure recovery devices, and as the industry had scaled and we learned all the tricks. But that we were approaching this dotted line here, the dotted line being the theoretical minimum amount of energy required to separate the salts from the water. And when you think about us being content with internal combustion engines that are 30% efficient, boy, getting to 60 or 70% efficient in desalination seemed pretty good, and it was hard to imagine doing much better. But then I started thinking about the fact that it's not just energy that's involved in desalination and delivering water to people. It's a lot more than that. So if you just think about the cost of delivering desalinated water, you can see that about 40% of the cost is the energy. But the rest of it are things like capital costs and running the treatment plant. So right away you could say, okay, if I want to get 40 or 50% reduction in the cost of delivering people desalinated seawater, I have to take a bite out of all of these different pies. And I think that that's possible. And then the other thing that you don't see when you look at kilowatt hours per cubic meter are the possibility of saving money by thinking about how a desalination plant fits within the grid, and the fact that the cost of electricity may be coming down in the future. That changes the calculus. It doesn't matter, same number of kilowatt hours per cubic meter, but cheaper water to deliver to people if we succeed in the solar and wind energy innovations that we're taking up now. So suddenly the picture changes. Let me give you 3 examples of how I think we're going to start reducing the cost of desalinated seawater and delivering it to people. I don't think these are absolutely the be-all and end-all. They're just illustrations of the kind of strategies we might use. In fact, I'm looking to a group like this to come up with the true innovations that are going to make it through and make this possible. First one, reducing energy use in reverse osmosis. So we heard a little about closed circuit RO or batch RO. And if you've read about this or thought about it at all, the theoretical reduction in energy to desalinate water by using CCRO or batch RO is somewhere between 37 and 64%. So suddenly that dotted line on the previous figure, which was meant for the typical way that we run reverse osmosis membranes now, it could be different. So I'm not saying that this is absolutely going to get us there, but there are innovations in process engineering that could start making reverse osmosis less energy intensive. And we've been surprised in the past by these innovations. It's not far-fetched to think that we could reduce energy use in desalination by another 30 to 50%. Here's another example. This is the Deepwater Desal project. It's a proposed project near Monterey in California. I'm not sure if it'll ever be built, but it's illustrative of the ways in which we can think about seawater desalination plants. This proposed desalination plant takes advantage of several facts about its location. First of all, it's got an intake pipe that's deep in the ground, sucking up cold water, which has fewer marine organisms and fewer nutrients that will cause fouling in the membranes. But more importantly, they bring the water into the treatment plant and they run it through a server farm to chill the server farm. So you get the energy of the cold water is doing cooling for you and offsetting some of the cost. And then the plant is co-located with a power plant. And in California, we have the so-called duck curve going for us on the grid because we're producing so much energy from our solar farms during the daytime that the cost of energy goes up and down over the course of the day. And just like they do in Israel at Sorek, you can run the desalination plant at higher and lower production to take advantage in changing costs of the energy. So same number of kilowatt hours per cubic meter, but less expensive desalination. So that's an example. And my final example isn't really an example at all. It's just an illustration of the age of manufacturing that we're entering. So the people in the manufacturing sector talk about Industry 4.0, the idea that we are going into a new generation of manufacturing where with additive manufacturing and sensors and artificial intelligence, we have the ability to tailor the way we build things. And so that means that we're primed for innovations in the way we build membranes, in the way we build microfilters, and in the chemistry that we use to make these things function. So I think anyone here who's an optimist, anyone here who's been around technology for a while, anyone here who takes a long view will probably agree with me that over the time course of 3 decades, it seems quite likely we're going to see significant reductions in the cost of delivering people desalinated seawater. Now, we could probably run a similar exercise for potable water reuse, for inland brackish water use, for conservation and other ways of saving water, and see that we can tighten up our water systems and reduce the cost and make them accessible to people now who find them out of reach. So I think that's amazing because we start bringing more people into this world of being able to afford these technologies. And I've grown your market for you, right? Your market was capped at about a billion people. Now I've got you a couple more billion people who might actually want to buy the things that you make. That's pretty good. Well, one of the things that drove a lot of us to think about water, one of the things that drives charities to think about water, are providing water for the world's poor. These are the compelling images of the people who can't afford to put in membranes and expensive systems. And these people are still going to be there 30 years from now, unfortunately. There may even be more of them if climate change and political instability grows. And so I think it would be irresponsible not to think about how we could bring these innovations to them and help solve some of these problems. And I think that this is an area that still needs a lot of work, and I think it's not the first problem that technology will address. But I want to give you kind of a few of my current thoughts about them. So one of my current thoughts is, I think like you do about the potential for distributed treatment technologies to provide solutions for people in low-income countries. And this is a figure from a paper that we published, a feature article in Environmental Science and Technology a couple years ago that the team out of Rice's Engineering Research Center, ReNUWIt, had led. But we think about the same things you do. Modularizing, miniaturizing some of the treatment technologies that we're developing and being able to deploy them in low resource type communities. But personally, I'm not entirely convinced. I'm not entirely convinced that we're going to have advanced oxidation processes providing water for people who have less than $1,000 a year to work on. So I think there's still more work to be done. There still needs to be better business models. But these things can start competing with the water delivery trucks. They can act as adjuncts to the ways in which we provide water now for people. And I think that this is an area that will continue to grow and be fertile. The other area that I think we often ignore because we tend to be technologists, we tend to be bound by the way in which we build treatment plants in wealthy countries, is to use natural systems for water treatment. So things like constructed wetlands and soil aquifer treatment can play a huge role in providing inexpensive, potable quality water. And anyone who hasn't thought about that should take a closer look at the Trinity River system in Texas, where just conventional wastewater treatment plants, constructed wetlands, and conventional drinking water treatment plants run one of the largest potable water reuse programs in the world. Now, I also want to say a couple remarks about one thing that tends to confuse people when we start talking about people in low-resource situations, the poor of the world. There's a second challenge that happens in parallel to the water supply challenge, and that's the sanitation challenge. There are a lot of people in the world who live in places that lack sanitation. I think we heard 2.3 billion or something like that earlier today. There is a sanitation challenge, and I'm a big fan of the approach that the Gates Foundation is taking with Reinvent the Toilet and a lot of these bottom-up approaches, and I think they will start having an impact in the coming years. But just remember that solving the sanitation challenge, not committing to sewers for human waste, is part of a solution, but it's not a solution that's going to provide drinking water to people. So these places are still going to need a drinking water supply, and these distributed bottom-up solutions don't yet show a lot of potential for providing a drinking water supply. It's also important when you set your sights bigger than just water for people who are wealthy living in cities to think about water for food. And I think I could talk for a long time. I've been spending a lot of time reading about water and food and the water-food nexus and all these other kinds of things. But I wanted to share a couple thoughts with you that I don't see people talking about in the literature. I don't hear people talking about a lot at conferences. So this is kind of the introduction and the overview, and maybe we heard a little bit about it before. When we grow food either in rain-fed agriculture or irrigated agriculture. In the next 30 years, we're going to have to grow about 70% more food to feed people. So people are getting wealthier, they're getting hungry for more meat, populations are growing, we're going to need to grow food, and we're going to need to do that while the climate is changing. So you can see in this figure, it shows you the parts of the world that already have irrigated agriculture in blue, and the parts of the world that rely upon rain-fed agriculture in green. So what do I think is going to happen over the next 30 years? Well, I think we'll probably be building more reservoirs to replace rain-fed agriculture with irrigated agriculture. I hope we do that right. I hope we don't damage the environment in a catastrophic way as we do it. But moreover, we're going to be intensifying the way we do irrigated agriculture. So the example that we see in Israel with fertigation being used to raise productivity of crops, or the precision agriculture movement where we put sensors in the soil and use them to grow food more efficiently. Absolutely, that's going to happen. But we're not going to use that for growing wheat. Wheat will probably still be rain-fed. We're still going to, the grains that feed people are still going to be grown in kind of the old-fashioned way. And so it's going to be a challenge, but it's not just a water challenge. It's a soil challenge, it's a plant breeding challenge, it's a labor challenge, and it's a global market challenge. So don't think that we're going to solve the world's food problems simply by solving the water problem. But that said, I think there's something that as a water person I come at, and I'm always a little puzzled why it's not discussed by the agronomists and the hydrologists. And that's this idea of what happens to the water. So when you take a hydrology course, one of the first things you learn is the difference between consumptive and non-consumptive water use. But when I see it as someone who thinks about mass balances, I think about useful water and wasted water. Stick with me for a minute on this. So if you're growing crops, water that ends up in the crop at the end, like the watermelon, it's full of water, that's not wasted water. That's water that goes into your product. And the water that went out the stomata through evapotranspiration, that's not wasted water. That's water, that was the price of doing business. And the water, when you do flood irrigation, the water that percolates into the aquifer that you pump back up to the surface the next year, that's not wasted water either. That's water that's staying on your farm. And so the only wasted water is the water that flows off of the field. And we call that agricultural runoff by tradition. But as an environmental engineer, I feel compelled to call it agricultural wastewater. And the reason I call it agricultural wastewater is that it's not pure water anymore, it's polluted water. And so when we look around the world and we see algal bloom, so I put a satellite image here of Lake Erie during the algal bloom a couple of years here, it's causing all kinds of problems. This agricultural runoff and the nutrients in it are causing toxic algae blooms that are affecting people's water supplies and making people sick, and causing dead zones in the Gulf of Mexico and off the coast of the Pearl River Delta. Well, I'm an environmental engineer. I see wastewater causing a problem downstream. What do? Treat the wastewater, and this is what agronomists have been doing for many years. Agricultural engineers, they build ponds for retention ponds to collect phosphorus. They build wetlands to remove nitrate. We can do that. We could do that probably with a greater efficiency than people who were studying it 30 years ago and just hoping for the best could do. We could intensify the way we treat this agricultural runoff and prevent some of these downstream solutions, but that's not how environmental engineers think anymore. Environmental engineers think about wastewater becoming a resource. So what if we could start to reuse the agricultural runoff on our farms and close the loops and grow our food that way again? Now, today, when we sit here in this room and we're struggling to just think about reusing water in a high-value operation, like a manufacturing facility, and it's barely something we can do, we think that would be crazy to do on the farm with all that water. Well, I don't think it's that far away. Maybe some of you heard about WaterFX, the company that got started a few years ago. I think it's not making it these days, but the idea here was maybe before its time. This idea that agricultural runoff could be treated, in this case they were planning to treat it with parabolic mirrors and distill it and manage the salt and everything else, but that may be something that we see in our future as an adjunct to solving some of these agricultural water issues. So, in summary, and I really want to hear what you all have to think about this over the break later. The BlueTech Solutions, the things that we're all doing in this room, that you're doing, that the early adopters are adopting and running with, they're enabling water solutions in wealthy places. I don't really worry too much about big cities in North America and Australia and Europe. They're wealthy enough to pay for the solutions to their water problems. But like other technological innovations, whether it's the iPhone, which then was adopted by people in less wealthy countries to gain information about agricultural prices or to do telemedicine, they're going to be repurposed, and people are going to use them for other applications that we can't even think about yet. So research and development is needed as a first step to drive down the costs of desalination, water reuse, resource recovery, and closing the nutrient cycle. And I think there are some key concepts to keep in mind as we move forward that I didn't really have a chance to dig into here. One is thinking about modularity, making sure that when we build water technologies, they fit together and each one is not a separate design challenge. Systems level thinking, I showed you a couple of examples of systems level thinking, like when you build a desalination plant and think about how it fits with the grid, or how the cold water could be used for another purpose. These are things that are really part of making a technology fit in a complex system. And then finally, the last thing is this idea of communicating successes and vision for water systems, because things like this meeting, things like the BlueTech movie, any way that we can tell this story to decision makers, politicians, and members of the public will build support and help people see this positive message that we can solve the world's water problems. Thank you very much.